European seminar.
Yeah.
We're very happy you accepted.
This is the good thing. Well, maybe the only good thing about this pandemic is that things get more global in some sense. So we have speakers from all over the world. So that's
it's much easier. And for us, parents of small children, it's much easier to give talks.
Yeah, I can imagine.
That's true. Well, it's interesting that you say that, because somehow if you work from home, then small children can also be quite an obstacle to giving a talk.
Certainly. Thankfully my building has this room downstairs where I am now, so that when the baby wakes up, my husband will take care.
Oh, okay, fantastic. That's excellent. Where do you live? I mean,
in Chicago.
Oh, that's what I thought. But and I heard that there's quite a bit of violence in Chicago at the moment.
Yeah, I think it's getting a little bit rough. We're downtown, so we're in one of these big high-risers with a lot of security everywhere. It feels very safe, but yeah, and we're still isolating. We've been isolating since March.
Oh, yeah, well, we're still isolating. But I'm just looking at the time.
I'm just
do you want to
everyone
now stop the screen sharing and we'll let everyone in?
Yeah.
Video.
Okay.
I just put the YouTube link also. There will be a live stream on YouTube.
We're very nicely organized.
Yeah, we're using the hospitality of the ICMS in Edinburgh, which is very professional in these things. So let's see how many people we have. Okay, I think the time is there. So welcome everybody to our, for the moment, last edition of Lagoon. Before the summer break, we will start again on September 3 with a talk by Andrea Solotar. And you can follow our webpage to see all the following up talks after that. We have already some scheduled, and there will be more scheduled when we get more speakers. Okay, as usual, let me just remind you, please mute your microphones. If you have any questions, we have, I think Laura will be happy to answer questions afterwards, so maybe also in between, if you put it in the chat, then we can react on it. And yeah, so as usual, please mute your microphone if you can. And so now it's a great pleasure for me to welcome Laura Shaposnik from the University of Illinois at Chicago. And she's going to talk on generalized hyperpolygons.
Thank you. Let me just share my screen. Sorry, I'm going to put it in full screen. Oops. You can see it well, right?
Yeah.
Yeah, okay, great. Thank you very much. Thank you, Sibyl and Frank, for inviting me to give this talk in your seminar. My screen, my video might interfere with my sound, so I'm going to turn my video off, and I'll be back for any questions. You'll be able to see me, but I'll stop my video for now. Okay, So what I want to tell you today is about some work that I've done with Steve Ryan that we finished recently, and some follow-up projects that we're working on. And this is on generalized hyperpolygons, which are defined through a special type of quivers, and which we introduced in our last paper that will appear soon in the quarterly journals of mathematics. So you can see the references here in this slide. Time permitting, I'll be finishing the talk by telling you about some of the current work that involves the applications of these hyperpolygons and quiver varieties to mathematical physics. Okay, so let's take a look and start with what I would like you to tell us the plan of today. So let me just put it like this. And the plan of today is the following. First, I want to tell you about these main objects for the talk, which are hyperpolygons. These are generalized hyperpolygons. Hyperpolygons were defined a few years ago by Ryan and Fisher, and they were interesting because they were related to Hitchin systems. But I want to first introduce them, and then I want to consider the relationship with Higgs bundles and Hitchin systems. And in this generalized setting, since this is one of the main reasons I started thinking about the topic. Then I would like to look into the appearance of integrable systems within spaces of generalized hyperpolygons. And finally, I'd like to consider hyperkähler structures. And within hyperkähler structures, how different spaces or different branes appear inside the moduli space of hyperpolygons. So even though many of you will have already worked on quiver varieties and there will be experts in the subject here, just to make sure we're in the same page, I want to start from the very beginning and looking at details of quiver varieties. Because the moduli space of hyperpolygons appears as the Nakajima quiver variety of certain type of quivers, the ones that are star-shaped quivers. And since I'll be using a very similar construction when considering hyperpolygons, I want to do a quick recap of how these varieties are built. So we will be generalizing this setup. And for these, the easiest or the nicest thing to do at the beginning is to take the simplest type of quiver that we can think of and that makes sense for our setting. So let's take a quiver, which is an A1 quiver, we call it, that just has two vertices, U and B, and has labels RU and RV over each of the vertices. And the space of representations is defined as the homomorphisms between C to the RU and C to the RV. So we have this space of homomorphisms. And considering the corresponding Nakajima quiver, which is the double quiver, we can now interpret the space of representations as the cotangent space of those homomorphisms. So we add an arrow going the opposite direction. This can be viewed as the direct sum of two spaces now of homomorphisms between the copies of C. And they're parametrizing the two arrows, where we think of the reverse direction as being the y direction, as being the cotangent direction. So let's put some labels here, the y and the x. And we think of these as parametrizing those spaces. To construct the corresponding moduli spaces, we're going to consider symplectic reduction, which will be then used for generalizing the setting to generalize hyperpolygons, where I'm not looking at star-shaped quivers, but a bit more sophisticated. So where does the symplectic reduction come from? For the symplectic reduction to each quiver, we're going to associate a real and a complex moment map that we're going to call mu and u, that takes the space of representations of a double quiver to the dual of the Lie algebra of its complexification. Oops, sorry. I'm going to mute you. These moment maps are associated with the complex joint action of a group G built from the action of groups on each of the nodes. And this is what we have, the mu and the nu. And on the non-central nodes V, we have the action of U of RV acting by left or right multiplication. And on the central node, we have the action of SUR. So here I'm going to write down the group so that you can see it. And these are the actions for the central node and the actions for the non-central node. Okay, so the useful thing will be to consider examples so that we can see how this is working. So next, I want to take a look at our little quiver and see what's happening here. And I put your the speaker down so that it doesn't make noise for you. But so if there's any questions or any comments, please put a sign, like you can raise the hand or something, and then we'll talk about it. Okay, so because we're defining these actions node by node, like we said before, we can build these maps over a whole quiver in a natural way. And to understand these moment maps, we can consider again this two-node quiver that I just wrote here. And in this case, the real moment map on X and Y is the difference between X star and X and Y star, where the asterisk here means conjugate transpose, as usually. And we can pretend it lives in the correct Lie algebra by scaling it appropriately. The complex map is just the product of X and Y. And this is what we have for the complex map. So this is the two complex maps for this example. The Nakajima quiver variety, when we want to form it with this symplectic reduction, we are considering it of a quiver, and it can be constructed through these moment maps, and it's an affine hyperkähler variety. Given a quiver Q not yet doubled, we're going to first consider the quotient of the space of representations by the group G that we wrote before, and this G will be a product for each of the nodes because we were doing it node by node. So let's take a look at how we can write that. We're going to consider it node by node. So this Nakajima quiver variety, we're going to quotient the space of representations by the group G, and we're going to put G as a product of all of these groups that we mentioned in the example, node by node. So it's going to be GL of RV for each of the V's that you have in your quiver. And then to obtain the Nakajima quiver variety, we are going to restrict the dual of the representation variety to the intersection of two level sets. And these two level sets are going to come via the moment maps. And then we're going to take the hyperkähler quotient that we're going to denote with these three bars. So we restrict the dual, we first put the dual, we restrict it to these two level sets. And it's going to give us our space. Now our group is going to be taken to be the product of the maximal compacts for each of the vertices. And the two level sets of the real map for a central element alpha that I wrote here, and the level set of the complex map around at 0. And the space has a very nice geometry actually, because from work of Hitching, Carlhead, Lindstrom, and Roek from a few decades back, the space has a hyperkähler structure where I, one of the complex structures that we can call I, comes from the moment map mu, and J and K comes from the moment map mu. So each of these two moment maps are giving us some of the complex structures that are needed for understanding our hyperkähler structure of the whole moduli space. Okay, so here we're talking about quivers and Nakajima quiver varieties in general. I want to start looking at generalized hyperpolygons. So first we're going to talk about hyperpolygons and then generalized hyperpolygons, since those are the objects that we are most interested in right now. So our interest is on generalized type of hyperpolygons, and hyperpolygons themselves, without the generalization, are built from A-type quivers. And let's just look at the simplest case first of a flag variety. So this is a flag variety that comes from choosing an A-type quiver with M nodes, as we have here, with labels 1 to R and integers in between in increasing order. And now the Nakajima quiver variety is given by the dual of the flag variety. So we double the arrows and we get the Nakajima quiver variety. Here we consider the underlying R as a vector of labels of our quiver, and then the integers 1 to R. The groups in question here, which we use for moment maps in this case, are G, which is the product of the URs for the vertices quotient by ±1, but not the one from the highest label R, which is the center, which is the sum of the dual of the Lie algebras for the non-central nodes. So let's put them here and try to write the groups that we need for these Nakajima quiver variety. So we have this cotangent of the flag varieties, and we have this G that is the product of the U of Ri's, but we're taking all of the Ri's except for the what we call the central node, which is the highest, which is R, and then we have the center of the dual of the Lie algebra, and that's the sum of these Lie algebras. So for our moment map, we're not going to consider the level set for which comes from all the nodes except for the central node. We're going to take them all to be 0 except for the node with a 1 that we put there. Sorry, just went too fast. And that's going to be alpha. And moreover, this space, it has a UR action, the central node itself, with complex moment map nu, given by the product of the 2 arrows to and from the node with nilpotent image. So this is going to be just on the central node, and it's going to be applied to the 2 arrows that comes. So this is xm-1 and ym-1. Those are the 2 arrows that touch the central node R, and this is just the product. We can use this analysis now to understand star-shaped quivers by putting all of these together, and then look at generalized hyperpolygons, where I'm looking at irregular star-shaped quivers with loops added. So that's where we're going. So as mentioned before, hyperpolygon space arises as the representation space of star-shaped quivers. And these are built by considering n many different A-type quivers, not necessarily with the same flag, joined together at the central node, to which we usually give the label R. So this is, I put here 3 and some dots, and we're going to put some labels. And so to build this space of generalized hyperpolygons, we need to first add G many loops to obtain a comet-shaped quiver. So I have the labels R and the central node, and I have these R sub numbers and upper script numbers, and these will be labeling each of the arms of the star-shaped quiver. And now we're going to add one more feature. We need to add loops. So we want to add the loops at the central node, and these are going to be G many loops, and the G should remind you of the genus of a surface, and that's why we're putting G. Because we're going to try to relate this to geometry of surfaces. So these are my G loops in green. And now that we have the G loops, we want to consider the Nakajima quiver variety for this. So once we added the loops, we're going to call this a comet-shaped quiver. And this is what's going to give us generalized hyperpolygons. So then we want to study Nakajima quiver varieties. So to define the Nakajima quiver variety of the comet, we do it as the dual of the product of the dual space of the flag varieties for each of the arms. So we did it for one arm in the example. We took the dual for each of the arms together with the cotangent space coming from the nodes, quotiented by the action of SUR. So let's just put it here. We're going to have all of these labels. So we're going to call R1 underline and to Rm underline, then all of these R vectors. And we're going to call alpha I the alphas that will give us the level sets to take these quotients arm by arm. And the loops will come from an SLR action and there's going to be G of them, and we're going to put those here. So let's put the group that we're going to use. Let's put it here with all of these groups, with all of these data, pieces of data that we have. So we'll take this cotangent of the flag varieties, and the flag varieties will be for each arm with these R upper one underlined to R underline subscript N, and we have all of them together, product, and then we need the loop input, and the loop comes from these SLRC action, and there's G of them, so we're going to have the tangent of SLRC to the G. Now we do the hyperquadratic quotient, and we're going to have these SUR action, and the quotient is taken via the moment maps, just as before, and we're going to consider the level set of 0 as well as of the parameter alpha, but now we have an alpha for each of these arms, so we have this alpha 1 to alpha n. So let's take a look at the moment maps to construct the appropriate moment maps, because this is something that we don't have, and that's one of the things that's been the trickiest, is to understand which moment map do we need to use to get an appropriate moduli space with good geometric conditions. For this, it is useful to understand how the loops of the comment contribute to the action. And so let's look at this example. At the central node, say that we call it star, we have n arms indexed by I and g loops indexed by j. And one can express the moment map as follows. We're going to suppress the indices just to make it easier. So let's call it yi and xi and get the following. So this is at one arm. The drawing that I made here is just for one arm of our generalized hyperpolygon. Okay, we have these loops and we have these arms. And the real moment map mu at star is the sum of the real moment maps at each of the arms, summed to the commutators of a loop arrow and its reverse one for all of the loops at the central node. And note that we're taking the traceless part, so we mark it at 0. And then we have the complex moment map. That's some of the complex moment maps for each of the nodes of the arms and by the commutators at each loop is doubled. And the generalized hyperpolygon space is then constructed through the level sets at 0 of the corresponding complex and real moment maps and modding out by SUR. So we equate them to 0 and then we mod out by the action. And it can be shown to be a hyperkähler variety of complex dimension 2 times the sum of the dimensions of the flag varieties. So let's just write down here, the complex dimension is 2 times the sum of the dimension of the flag varieties plus g minus 1 times r squared minus 1. So when we're looking at a smaller case or a simplest case, for instance, when all of the flags are complete, so when we have from 1 to r as our labels, we recover the expected dimension that you may have seen before, and r times r minus 1 plus 2g minus 1 r squared minus 1. Anyway, this is just one case in which something particular happens, where like all the flags are complete, but we're interested in more generic settings. And we do wonder what geometry starts arising from these objects now that we have moment maps. And geometrically, we can think of the spaces of generalized hyperpolygons as parameterizing pairs of polygons whose sides have lengths determined by those values of the moment map. These are in close analogy to polygon space, where you get from star-shaped quivers polygons. And in particular, since we're working with arbitrary genus, we're going to get 2 different sizes of polygons. We're going to have a 2n plus 2g gon, and then an n plus g gon. So here on the left, we have the 2n plus 2g gon and the n plus g gon, and all of these sizes of the edges arise from the moment map that we have equate them to 0, and so we're sure that these polygons close. So geometrically, this is the interpretation that we can think of, keeping in our head. So for hyperpolygon space, we're going to call it like this: x sub r over G. The G is going to give us the genus. It's going to depend on alpha, which is our parameter. We're going to say that it's a space of generalized hyperpolygons of length alpha. So alpha will be our hyperkähler parameters. And hyperpolygons themselves, without the generalization, they were first studied by Kono as a natural hyperkähler extension of our usual of the usual polygon space. And this was some time ago. Later on, it was continued to be studied by Harada and Pruitt as a Nakajima queer variety in a much more detailed version. And these spaces were more recently shown to be very closely related to Higgs bundles. So closely related to Higgs bundles. And this was first seen for genus 0 by Godinho and Mandini for rank 2. So rank 2 Higgs bundles and genus 0 surfaces, and later extended to any rank by Fisher and Ryan, still with genus 0 and with minimal flags. So the flags had only one vertex, and we had genus 0. So with Steve Ryan, we wanted to now consider the case of Higgs bundles in general with surfaces of arbitrary genus and their relation to hyperpolygons, and hence we needed to have any type of flags and somehow encode the genus, and that's how these loops appeared and any type of flags appear, leading to some nice relations to Hitchin systems. So I want to tell you a little bit about Hitchin systems and how, or Higgs bundles, and how they relate to these hyperpolygons. And this is what we're going to be doing next, since one of the inspirations for me to work on the subject. Okay, so what is the relation between generalized hyperpolygons and Higgs bundles or Hitchin equations? Nakajima quiver varieties, remember that it can be thought of as a finite dimensional analog, actually, of Hitchin systems. If you haven't seen Hitchin systems before, recall that Hitchin systems equations, what they're doing, they're expressing both the flatness of an SL and C connection and the harmonicity condition for a metric in a resulting flat bundle. So you have flatness of a connection and harmonicity of a metric. In particular, this appears from the two equations obtained via a real and a complex moment map. So I want to look at that. So we have these two equations, two moment maps equations for which we consider the 0 level sets, so equate them to 0. And I want to reorder. So let's take the moment map themselves away and reorder these. So I want to reorder the two equations so you can see what they're meaning. And what we're going to see is that the failure of a polygon to close is corrected by the choices that we make for the cotangent data, so that y data, that double arrow. And this is very similar to Hitchin's first equation, where the failure of the curvature to vanish for the connection is measured by the choice of the Higgs field phi. And this is what we're going to see here in these equations. So now we remodify these equations, and we see that there is a failure of a curvature. I'm going to write down here Hitchin's equations, which is f of a plus phi wedge phi dual equal to 0. And this is very similar to this first equation, where we're looking at failures of polygons to close or failures of the Higgs field. So failure of the curvature to vanish. The second, now that we know which part corresponds to each part, so now that we have a connection part and a Higgs field part in the first hyperpolygon equation, we see that in the second equation, the connection part was acting on the cotangent data. And so that was the analog that you could very quickly try to see. We can go over it later. So now I want to associate Higgs bundles, and we can associate a corresponding Higgs field by considering a puncture surface. So let's consider D a positive divisor in the upper half plane, which we're going to tile with puncture 4G guns. So we're going to put here the upper half plane, And we're going to use the X and the Y data to define the residues of the Higgs field. So it's going to be meromorphic now, because we're going to have these 4 gigons that I'm drawing here in violet, and they're going to be punctured with our points Zi, and those Zi have to give some information to our Higgs field. So choosing, we're going to choose some nice function appropriately. We're going to be able to actually give this Higgs field, this meromorphic Higgs field, a nice one-to-one correspondence to the space of hyperpolygons. So let's write it down here. The Higgs field, then it can be defined as follows. Let's write it here. It's going to be a quotient where we're going to have the following information. We're going to sum over each of the arms. Well, we're going to sum over, we're going to have also these ZIs. So really the ZIs are going to be the important part here. The function gz that I'm going to write now is going to be the important part. So we have the xi's and yi's that were our arrows for each of the arms, and then we have z minus, and now we're going to have this this modified version of our zi's, our puncture spaces. And defining this g of zi as a quasi-periodic function is that we can form the quotient in a well-defined manner. These are Higgs fields for the trivial rank R bundle on those surfaces, and compactified, we to compactify before we take the quotient so that we get a compact Riemann surface. And this embedding that we're going to take is going to respect the complex structure I, but not the J and K. So this embedding of Higgs bundles within hyperpolygon space is not going to be a hyperkähler embedding. So it's not that we have a hyperkähler subspace. We just respect one of the structures here. So I want to take a look at an example now. Since here we did Gino 0. So let's take a look at an example in the case of hyperpolygons with minimal flags. And so we're having to have Gino 0, so no loops. For this, I want to consider a affine D4 Dinkin diagram. So I'm going to put one central node and then 4 other nodes coming here. Minimal flag, which means our arms are going to have sorry, labels 1 and 2 because they're minimal. And all of the arms are going to have the same label. So we're going to have 1s everywhere outside, 2 in the middle, and our vector, our i's are 1, 2, which we can put square bracket 2. And we can double it to get the Nakajima quiver. And we can consider the space of hyperpolygons, which is this X that in our notation is 2, 2, 2, 2, 2, and label alpha. So what we know of this one is that the model space of hyperpolygons in this case is a K3 surface with a complete ALE metric, and it's a gravitational instanton. It embeds into the Hitchins system of parabolic Higgs bundles of rank 2 on P1 with 4 punctures, and this gives the 4 punctures give 4 tame singularities to the Higgs field. This is really the examples that were studied by these people that I told you worked on hyperpolygons before. So Godini, Mandini, and Ryan and Fisher, they were looking at rank 2 objects with minimal flags. This is what a minimal flag looks like. And the embedding is not hyperkähler, like we mentioned before. It's not a hyperkähler varieties. The difference between the two spaces is exactly of codimension, is a codimension 0 subvariety, and it can be thought as the Hitchins section. This puts us in contact now with Hitchins integrable systems. So the difference, what you can think is the difference in the hyperkähler structure as measured by the metric in the space. So for alpha equals to 0, which is non-generic, you get a symplectic singularity, which is a Kleinian singularity, actually. So since we're coming to Hitchins sections and Hitchins integrable system, we ask, is there something similar here? Can we, in more generality, for generalized hyperpolygons, think about integrable systems, which would be something very interesting. And yes, there is. So let me tell you about that. So given the correspondence between generalized hyperpolygons and Higgs bundles, we have looked into the appearance of integrable systems, which would be analogous to the Hitching vibration. And we want to do this for both hyperpolygons and generalized hyperpolygons. We need to keep in mind for as motivation for doing this, that back in 1994, Nakajima mentioned in his work that one would expect Nakajima query varieties to be completely integrable Hamiltonian systems. So for those Nakajima query varieties, there is a hint that things should work out. Even if it hasn't been proven, things should work out. Fisher and Ryan showed that this is the case. So for the cases that they worked on, so they showed that this is the case for hyperpolygons on genus 0 surfaces and minimal flags. And when the rank R of the induced Higgs field is equal or less than 3. So this is a particular case. Let me just write it down here. This is the case for genus 0. So we put the 0 upper script, minimal flag, which means we're going to have one as the outside node and R in the front, in the central node, and R has to be at less or equal than 3, and we have any arms, any number of arms. And they did this by embedding the space of hyperpolygons into certain space of tame Higgs bundles on the puncture sphere. So what we want to do now is extend this to any R, any G, any N. So try to generalize it as much as we can to get things on any genus Riemann, compact Riemann surface and Higgs bundles with any type of singularities arising there. And we can do it in some particular cases. We can now extend this to hyperpolygons where the comets have complete or minimal flags. So let's do that. Let's recall that the space of generalized hyperpolygons was obtained, like we said before, by taking the product of a flag variety and a quotient and a restriction via moment maps. So we're going to do that. The quotient can be seen to inherit the symplectic structure from the original product, but we want to know whether there's more. So let's write down the product, which is here. We have all these flag varieties, and we're going to take a quotient here to get our hyperpolygon space. And we're asking what happens to hyperpolygon space. Does the hyperkähler structure of the top also descend to the bottom? But we know some things here. We know that the flag varieties are integrable systems of Gelfand-Tyson type, and the component coming from the loop gives an integrable system of Lie-Poisson type. They have hyperkähler structures. And whilst we know that the bottom inherits the symplectic structures, we want to know if all of the upper integrable system structures also descend. So let's write down here the integrable system structures, the Gelfand-Tyson saline type on the left, and we're going to write the Lie-Poisson type on the right. So this is the saline type, and this is the Lie-Poisson type. And we want to ask if all of these integrable systems descend to the equation. And to study this, we want to see the appearance of the right number of invariants. So remember, we need for an integrable system, we need these commuting Hamiltonians, or these invariants that appear downstairs. So for these, we're going to consider generalized hyperpolygons which have C complete arms. So I'll put it in blue so we remember, and n minus C minimal arms. So only complete or minimal, C complete, n minus C minimal arms. And the minimal arms, remember, are just those that have two labels because they have two nodes, 1 and R. Within the complete arms, we have kth arrows. So we have arrows, and each of the kth arrows give us a k by k block. So remember, it's a map between vector spaces of dimension k. So we have k by k blocks contributing K invariants, and these will be the Hamiltonians for the Gelfand-Seidel systems. So these are the K invariants coming from there. So let's see all of the invariants that appear in our system to see how many there are. So from the Gelfand-Seidel type integrable systems, which give complete flags, I'm going to put here our Jones hyperpolygon on the right, so you remember how it looks like. And from these Gelfand-Seidel type integrable systems giving complete flags, we have the 1 plus 2 plus r invariants. And so multiplying by the complete number of flags, we have c times that. So we're going to put a c here in front of all of this sum. What we're going to get is the c times r minus 1 r over 2. So let's put it in blue, this, or in color, this c here, where c was the number of complete flags. So the ones that have all of the numbers, 1, 2, 3, up to r minus 1. So this is from the Gelfand-Seidel type. Now we have the minimal flags to analyze. And from the minimal flags, we have, remember, r minus 1 multiplied by the number of minimal flags, which is n minus c. And that's it from the minimal flags. And then we have to consider these loops that are in light violet, in lila, in the drawing on the right. And for each of the loops, we have r squared minus 1 for each of the loops, since we're coming from SLRC, and we have g of them. So this is the invariance coming from the loops. So now we have chosen many fixed parameters in our construction. We have chosen the R label of the central node, the N of the number of arms, the G, which is the genus, and the C, the number of complete arms. So for each of these choices, we can now show that there's a hyperkähler reduction by the SUR action, which fixes a number that I'm going to call NRN of RNGC of invariance. And the interesting part is this is also a hard number to get once we see what it fixes. The interesting part is that once we subtract those invariants to the total number of invariants we get half the dimension of hyperpolygon space, which is what we wanted. So this leads to one of our main theorems, which is going to say that the space of hyperpolygons is a completely integrable Hamiltonian system of Gelfand-Seidel type. So we summed all of these three numbers of invariants that we have. We subtract this number n of fixed invariants that we were able to find, and this is what's half the dimension of hyperpolygon space. So let's write it down here. Half the dimension of x upper G for our invariant G, the R labels for each of the arms, and the alpha that we have. So the theorem that we have now is that with Ryan in this paper that should appear very soon in the Quadrillion Journal of Mathematics, is that this is a completely integrable Hamiltonian system of Gelfand-Seidel type. It's a very interesting system in particular because of how it was constructed. So let me tell you a bit more about something that we find interesting about this system. What is interesting of this integrable system is that it shows the existence of sub-integrable systems within meromorphic Hitchin systems, which do not see the complex geometry of the algebraic curve. So we haven't used at all the complex geometry of the Riemann surface. This is something that should lead to some new understanding of the whole space of meromorphic Hitchin systems. This is a purely representation theoretic construction of sub-integrable systems. Remember that the Hitchin vibration is constructed heavily on using the complex structure of the Riemann surface, since the base of this integrable system is the space of differentials, holomorphic differentials on the surface. And moreover, through the hyperkähler structure that we have, we may consider the appearance of Lagrangians or complex holomorphic subvarieties within these integrable systems. And this is what leads us to understand the relation between hyperpolygon spaces and mathematical physics, and in particular the appearance of Lagrangians, which are what is going to give us branes within hyperpolygon spaces. So the last part of the talk, I want to dedicate it to understanding or telling you a little bit about branes. And recall that one, we have a hyperkähler variety, just any hyperkähler variety, not necessarily hyperpolygons. It has a quaternion ijk and corresponding symplectic forms omega I, omega j, and omega k. We can consider compatibility of subvarieties with those structures. So borrowing the terminology from string theory, but simplifying a little bit here, we're going to consider the following type of notation. And I say simplifying since we're going to forget about some higher structures appearing. We're going to say that a complex subvariety with respect to one of the complex structures is a B-brane. So let's put here a B-brane. These are going to be one of the objects we want to study. And we're going to say that a Lagrangian subvariety with respect to one of the symplectic forms is an A-brane. So this is the other type of space that we want to consider. And if you haven't seen this notation before, remember that Lagrangian has an A and A-brane has an A. So let's put the A for Lagrangian here as an A-brane. And we can have many types of branes because when considering the whole hyperkähler space, as it's a generalized hyperpolygon space as an example, one may find triples of branes of different types because we have 3 structures. And so we can have branes which have A's or B's for each of these 3 structures in the order that we preset before. And these are the following. They can be ABA branes, AAB branes, BAA branes, and BBB branes. And the order corresponds excuse me, to the order previously set for the IJK. And we want to find spaces which satisfy these relations. This is what we call with Ryan triple branes. And we want to find triple branes of hyperpolygon spaces. So we're inspired by work that we've done before. So for Higgs bundles without punctures, branes were considered first by Kapustin and Witten back in 2006 in terms of sigma models in their electromagnetic paper. And later on, together with my collaborators, we constructed the first large classes of branes via involution. So with Baraglia around 2013-14, and then using finite group actions with Heller a couple of years ago, and then with Heller and Biswas this year. We constructed branes which come in families, and they all come from these involutions. Involutions acting on the Riemann surface, involutions acting on the Lie groups, and finite group actions acting on the Riemann surface. So there's a lot of actions appearing that motivated the study of branes within Higgs bundles for me, and I wanted to see the same happening for hyperpolygons. So we want to ask which types of branes can we build now within the space of generalized hyperpolygons, and what are their dual spaces via mirror symmetry? Because that was one of the key questions that we were asking for Higgs bundles. What happens with mirror symmetry that relates types of branes from the physics perspective? Is there some duality between spaces of hyperpolygons that we haven't seen before here? Expanding on the work of involutions that I just wrote here in the second point, Victoria Hoskins and Florent Schaffhauser consider branes for minimal rank 2 and hyperpolygons on genus 0. So this first case that is the nice example that we mentioned before, that Godinho and Mandini and Fisher and Ryan had looked at, Hoskins and Schaffhauser consider branes appearing from there using some type of involutions last year, but very restricted type. So with Steve Ryan, we began by considering families of triple branes through involutions, but we wanted to stay away from what was done already. So we started to look at involutions that didn't fit the layout of Hoskins and Schaffhauser, but would encompass higher rank bundles. thinking that maybe their layout was what avoided, or the reason why higher rank couldn't be achieved. So I want to finish the seminar by telling you a little bit about how this can be done as an example, and then this will lead to our upcoming paper on that. So let me conclude by showing you one example of such brains. And you can see more in our paper that has the last section with this. And this example and a couple more. So consider the evolution on the space of generalized hyperpolygons, which negates the cotangent directions. So to negate the cotangent directions, we're sending an evolution that sends x, y, a, and b. Remember, the a and b's are the labels for the loops and the cotangent arrows of the loops, and we negate the cotangent direction. So it sends it to x minus y, a minus b. And the fixed point set of this evolution is given by precisely the hyperpolygons which have vanishing cotangent directions. So we put a 0 in the cotangent directions, and this is precisely the space of generalized polygons of the same length alpha. So whichever alpha we chose, that's the same that we have to keep here. And we have the fixed point set being the space of these generalized polygons, so not hyperpolygons. So let me just put a P for polygons for the same genus, the same Rs, the same alpha. So by considering the compatibility with the complex structures and the symplectic forms, we can now show that this space is a holomorphic subspace with respect to I, but it's the complex Lagrangian brane with respect to J and K. So it's an BAA brane within the space of generalized hyperpolygons. So let me just finish by saying that in our current project, we're constructing further types of branes of hyperpolygons and studying different dualities that arise through these constructions. And this should lead to some very nice relations between hyperpolygons and mathematical physics that we're very excited about. So thank you. Thank you for listening. I'm going to finish this by just writing that on the slide, because we want other dualities, and you'll see in our paper that there are some other dualities. So thank you. Thank you very much for listening. I'm going to put back my my screen if I can. If I figure out how to do this. Start video. And there we go.
Thanks very much for your very nice talk. That was great. Are there any questions? I can't see any questions in the chat.
I'll be very happy to answer questions also via email.
Yeah.
I know that's sometimes easier.
Yeah, if people are too shy to ask now, they can send you an email.
Yeah, you should definitely. And we have some more notes to share.
We'll ask about your nice slides. If you could actually send me out, then we can put them on the web page. Yes,
sure. I'll send you, as I said before, you saw that I've been erasing and resetting, so those things won't appear in the PDF. Yeah. But I'll send you the PDF for this, for the end of each slide.
That's great. I had actually a question. So if I understood correct, so you said that you normally don't get a hyperkähler embedding, or I wasn't completely sure under which conditions you get this hyperkähler embedding. What are the obstructions exactly here?
So the compatibility of the complex structures with the space of hyperpolygons, it's when you're looking at the quotient, the complex structures are not preserved, which is something tricky to show. So I think some people that have been looking at the lower rank had omitted this point. And so at the beginning for lower rank, it was thought that there were hyperkähler subspaces, which would have been very interesting, because then you're actually getting subbranes, because they're hyperkähler subvarieties. But once you start doing the calculations more precisely, you see that the complex structures are not preserved, and so the symplectic forms are neither. Yeah, so only the I, which is the one that usually we consider as the one coming from the Riemann surface, the complex structure of the Riemann surface. which is still very interesting because, like we said, the integrable system from the Hitching perspective relies heavily on this complex structure I. And even though this was preserved and we have an embedding on complex structure I, we don't use it to construct the integrable system.
I see. And the other question I had was, yeah, you mentioned that it doesn't